Okay, so now that we've had a broad overview of energy and matter, and we talked a little bit about what energy is, and then classification of matter, and physical and chemical changes, let's go back to the energy idea, and we'll discuss specific heat. So in our earlier discussion, we talked about kinetic energy and potential energy and temperature and thermal energy. And now it's time to focus on specific heat, which has a very distinct definition, and we'll see that it involves some mathematical relationships that will be able to relate materials with how much heat energy they absorb and release. Alright, so specific heat, as you see, is different for different substances, which is why we call it specific. It's specific to the material. It's defined as the amount of heat that raises the temperature of 1 gram of a substance by 1 degree Celsius. And I believe technically it's 34 to 35 degrees Celsius or something like that. It's even more specific a definition than we show here. It's represented by the equation specific heat, which is abbreviated in our text as SH, but you see it elsewhere with other abbreviations. And that's equal to heat divided by mass times delta T, where delta T is the change in temperature, T final minus T initial. In the SI system, the units we'll expect will be joules per gram degree Celsius, and in the metric system, we'll expect units of calorie per gram degree Celsius. So we will see the calorie, sometimes we'll see the joule other times, and based on our earlier discussion, we showed the relationship that 1 lower C calorie is equal to 4.184 joules. So we can go between the systems. It's just a factor of 4.184, which we would multiply the calorie value by to get into joules. Here we see table 2.8 from the text, which lists the specific heats of some substances. And so if we look, there's some elemental metals, and we see aluminum, which has a specific heat of 0.897 joules per gram degree Celsius. The calorie value, as we would expect, is different by a factor of 4.184, which would relate joules and calories. So if we multiply the 0.214 calories per gram degree Celsius by 4.184 joules per calorie, we get the 0.897. So we see there's a relationship there. And so that's a relatively higher specific heat than copper. Gold is even lower still, which is why gold would be the ideal conductor of heat and electricity, but of course copper is much more available and much less expensive than gold. So we go with copper, which has the lowest specific heat of the common metals that would be the least expensive option. If we look at some compounds, we notice specific heats tend to be much higher for the compounds. Sodium chloride has a pretty low specific heat. It's just a little bit lower than aluminum. So it's unusual in that regard. The other compounds that we see, water in particular, as you see, it's defined, the calorie is 1.00 calories per gram degree Celsius for water, and therefore it's 4.184 joules per gram degree Celsius. Alright, so before we do any heavy-duty math with this idea, let's pause for a brief learning check. We've got 2 questions here. First, if the same amount of heat is added, what will occur in a substance with a lower specific heat? A smaller increase in temperature, or B, a greater increase in temperature? You can think back to that graphic from the previous slide if you want to think about a lower specific heat. So just compare aluminum and copper, for instance. Copper had the lower specific heat, so what would we expect? For number 2, when ocean water warms, what happens to the surrounding air? Does it A, cool, B, warm, or C, stay the same? So think about these. They're not mathematical explicitly, but they are involved thought questions. So you may want to pause the video here, give them some thought, and then we'll move to the next slide to get the answer. Okay, so hopefully the first one was pretty easy. If it has a lower specific heat and we're adding the same amount of heat energy, then more of that is going to go into an increase in temperature change. So the lower the specific heat, the greater the increase in temperature if we're adding the same heat energy to 2 samples, for instance. So if we had copper and aluminum, and we added the same heat, the copper would undergo a greater temperature change because less of the heat goes into the specific heat of the material. Number 2 is a bit trickier. You have to really think things through here. So when the ocean water warms, what happens to the surrounding air? Well, as the ocean water warms, you've got greater evaporation of that ocean water, and also the air currents themselves. You're going to have a cooling effect on the air above it. So that's a lot more involved, and that one, if you missed and still are struggling with, you're going to be fine in the course as long as you're good with number 1. Number 2 was out there to challenge you, and hopefully it makes a little more sense that the warming ocean water would give rise to cooling surrounding air. Alright, so now that we've handled the theory and we've had a learning check with some thought questions, let's go ahead and talk about calculating specific heat. So like we've done before, we'll have an approach that involves multiple steps. In this case, we'll have step number 1, which is the same as we've always done: state the given and needed quantities. Step number 2, now we're going to write the relationship for specific heat. And then step number 3, set up the problem to calculate the specific heat. So let's consider the following problem. What is the specific heat of a metal if 24.8 grams of the metal absorbs 65.7 calories of energy and the temperature rises from 20.2 degrees Celsius to 24.5 degrees Celsius? So step number 1, we're going to state the given and needed quantities and analyze the problem. So we're given the mass of the metal is 24.8 grams. We're given the calories of energy, 65.7 calories. And we're given the temperature change from an initial temperature of 20.2 degrees Celsius to a final temperature of 24.5 degrees Celsius. What we need ultimately is the specific heat from that metal in units of calories per gram degree Celsius. Okay, so moving on to our next step, we'll write the relationship for specific heat, which is specific heat equals heat, in this case in calories, divided by mass times the delta T. So in step number 3, now we're ready to set up the problem. First, we have to consider the delta T. So 24.5 degrees Celsius minus 20.2 degrees Celsius. This is a subtraction, so we end up with the 4.3 degrees Celsius, the decimal place of least significance, the tenths place for each of those temperature values. Now we drop down to just 2 sig figs, 4.3 to the tenths place. And then if we take our 65.7 calories, divide by the 24.8 grams times the 4.3 degrees Celsius, we end up with 0.62 calories per gram degree Celsius. So we see that the sig figs are now limited to 2 sig figs because the subtraction rules told us we ended up with 4.3 based on the decimal place of least significance, the tenths place. Then we used that result in a multiplication division approach where the rules say the final answer should have the same sig figs as the least significant value. So 65.7 for the calories, 24.8 for the grams. Those were both 3 sig figs, but the delta T gave us just 2 sig figs. So that's why our final answer is 0.62 calories per gram degree Celsius. The correct units, the correct calculation, and the correct sig figs. So what if we're not looking for specific heat? What if we want to solve for the heat? If that's not given, like it was in the previous problem, we could rearrange that equation of specific heat to give us what we would call a heat equation. So this form of the equation would say that the heat supplied would equal the mass of the material times the delta T, the temperature final minus temperature initial of the material, times the specific heat for that substance. So the amount of heat lost or gained by the substance is calculated by knowing those quantities. So in this case, we know the mass delta T, or at least the temperature starting and final, and the specific heat in either calories per gram degree Celsius or joules per gram degree Celsius, and we can therefore solve for the amount of heat that would be needed to cause that temperature change. This means we'll modify our approach a little bit from solving for specific heat. Now, if we're using specific heat, we'd still take our first step, state the given and needed quantities, analyze the problem. Now, in the second step, we'll calculate the temperature change, because if we're solving for the heat, we should have both starting and final temperatures, initial and final temperatures. Finally, we'll write the heat equation, and then in number 4, our final step here, we'll substitute in the given values and solve, making sure units cancel to give the final correct units. If For instance, we're looking for heat in joules. We want to make sure that we have specific heat in joules per gram degree Celsius, or if we want final heat calories, then obviously we would want the calorie per gram degree Celsius form. Alright, so let's look at a problem. In this case, we have a hot water bottle containing 750 grams of water at 65 degrees Celsius. If the water cools to body temperature, remember in the Celsius system that's 37 degrees Celsius, how many calories of heat could be transferred to the sore muscles that hot water bottle was in contact with? So step number 1, state the given and needed quantities, analyze the problem. So in this case we're given the mass of water is 750 grams. We'll consider that 2 sig figs since there's no decimal point telling us that 0 is significant. We have the initial temperature of the water is 65 degrees Celsius. We have the final temperature of the water is 37 degrees Celsius. And what we're solving for is the calories of heat transferred. So we'll want the specific heat of water in calories per gram degree Celsius rather than joules for this problem. Okay, now step 2, notice how tricky this is. We're looking for the heat transferred to the sore muscles. So we're assuming that the final temperature of the sore muscles is 65 degrees Celsius and they started at 37 degrees Celsius. We're not looking at the water bottle, which went from an initial temperature of 65 down to 37. We're looking at the muscles, which we assume started at 37 and went up to that 65 degrees Celsius. Of course, we could have solved it the other way. We could have solved it for how much heat that the water bottle released and then realized that the muscles must have absorbed that. So we'd change the sign at the end for the heat. But this way, we'll avoid that final sign convention issue, and we'll get 65 degrees Celsius, what we assume the final temperature of the muscle to be, although it probably didn't quite achieve that due to heat loss, minus 37 degrees Celsius to get a total temperature change, delta T, of 28 degrees Celsius. Finally, now we can write the heat equation. Heat in calories equals mass in grams times the delta T times the specific heat, which we'll have to look up for water in this case. Okay, finally, as we make the substitutions, the mass of our water bottle was 750 grams of water times 28 degrees Celsius, the delta T for the muscle, and then times the specific heat in calories per gram degree Celsius, which for water is defined as 1.00, and we end up with 21,000 calories. Notice that the 28 degrees Celsius, that delta T, having just 2 sig figs, as well as the mass of the water bottle, which was sort of vague. Was it 2 sig figs? Was it 3 sig figs? Fortunately, it didn't come down to that. If we really wanted that to be 3 sig figs, we should have shown a decimal point for it. But either way, because of the 2 sig figs for the delta T, we end up with 21,000 calories of heat transferred. Okay, so now that we had a little practice together, let's follow up with a learning check. In this case, we need you to determine how many kilojoules are needed to raise the temperature of 325 grams of water from 15.0 degrees Celsius to 77.0 degrees Celsius. Is it A, 20.2 kilojoules, B, 84.3 kilojoules, or C, 105 kilojoules? So go ahead and pause the video here, take some time to work the problem, and then start back up and we'll see how you did. Okay, so we'll solve the problem as we hope that you did on your own by following the steps. Step number 1, state the given and needed data, analyze the problem. In this case, we're given the mass of water as 325 grams, the initial temperature of the water, 15.0 degrees Celsius, and the final temperature of the water, 77.0 degrees Celsius. Ultimately, what we're solving for, what we need, is the kilojoules of heat needed to cause that temperature change for that amount of water. Okay, moving on to step 2, we'll calculate the temperature change, delta T. In this case, the water is going to end up at a final temperature of 77.0 degrees Celsius minus its initial temperature of 15.0 degrees Celsius gives us a delta T value of 62.0 degrees Celsius. Moving on to the next step, we'll write the heat relationship. The heat equation here is heat in joules, because that's what we'll ultimately look for kilojoules, but first we'll solve for joules because that's what our specific heat would be in either joules or lowercase c calories. So heat in joules equals mass in grams times delta T times specific heat. Okay, so finally moving on to step 4, we substitute in those given values and solve for our heat energy, and finally in this case make sure that the units are correct. So 325 grams of water times 62.0 degrees Celsius, the temperature change for the water, times 4.184 joules per gram degree Celsius, the value for the specific heat of water in joules per gram degree Celsius, since we're ultimately looking for kilojoules here. And then finally the conversion factor, 1 kilojoule over 1,000 joules, right? That way we'll get grams to cancel, degrees Celsius to cancel, and joules to cancel to leave us in a final answer that's in kilojoules, and in this case is 84.3 kilojoules, which was answer choice B. So hopefully you were able to do this on your own after that one we worked together. If not, perhaps you just need a little more practice. Go ahead and try some end of chapter problems. I think there's 1 or 2 homework set problems that go along with this. And if you're still having trouble, then obviously reach out to me and I'll see what I can do to help you understand wherever you're having trouble in this subtopic of specific heat. So hopefully that's not the case. Hopefully you're doing quite well, and we can wrap up the specific heat topic and look forward to the final topic in Chapter 2.